My name is Harshan. This is my Lab 5 Magnetic Molasses Lab. So for the introduction, so the purpose was to collect data on a magnet falling through an aluminum tube in order to observe and apply Faraday's law. So the fundamentals were Faraday's law, the Biot-Savart law, Newton's second and third law of F equals ma, and opposite and equal reactions, Ohm's law, magnetic force on a loop, and the time derivative of magnetic flux of a dipole. And the results were, so the experimental time was 1.25 seconds and the computational time was 1.118 seconds. And as you can see, I have different pictures of the different laws and different laws of the formulas that we would use. So the models and assumptions. So the models were the magnet was used to model a magnetic dipole while the aluminum foil modeled a tube through which it fell, and the assumptions were air resistance acting on the falling magnet is negligible, and gravity and the magnetic force of the aluminum tube are the only two forces acting on the falling magnet. So the experiments, the system was the aluminum tube and the magnet. So the surroundings were everything else. And so the procedure was first using the magnetometer on my phone. I marked the north and south pole, marked the north pole of the magnet. Then setting up the camera to record, I dropped the magnet through the aluminum tube 5 times. I used the video footage to calculate how long the magnet took to fall through the tube for each trial. So these were the measurements. Dropped it from zero point 0.3 meters. The width was around 0.006 meters. Inner radius was 0.024 meters. Radius was 0.03 meters. Mu, we used from lab 3, which is 2.12 or 2.21. Magnet's mass was 0.025 kilograms, and the average time was about 1.25. And as you can see, these are my different trials. So this is the video experiment. I didn't include all of them, but these are the two video experiments basically. Now next is the glow script code. So this was the code of the glow script that I had. And there's like a couple more lines, and this is kind of the final line of the glow script code. And this is the visual. As you can see, this is so the left picture is it fully ran, and the blue bar kind of at the bottom, and this is like the velocity versus time graph on the right. The discussion. So model discrepancies, there were none. Sources of air, we're considering air resistance likely was negligent. The only source of air was likely human error and incorrect value from mu due to like the error of lab 3. Now this is the what if question. So what if the resistivity of the conductor were reduced to as close as possible to zero? How would the dynamics of the falling magnet change? So the dynamics of the falling magnet would change significantly. So the eddy currents, which normally oppose the magnetic motion, will be minimized, allowing the magnet to fall faster with less resistance. Additionally, in a superconductor, the Meniser effect could cause a magnet to levitate or be repelled, potentially altering the falling motion entirely. And the next one is what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So if holes or slots were cut into the tube, it would like disrupt the flow of the induced ring currents. These interruptions would reduce the strength of the eddy currents, potentially weakening the opposing magnetic force that slows down the falling magnet, causing it to fall faster with less resistance. Thank you for listening.